Welcome to Strength of Materials N6. Today's video is a special one because we're going to look at shear stress in beams. The reason I say it's special, it's because ever since the beginning of 2023, we are no longer using the old syllabus. They have changed some of the modules, they've removed some, and they have added new modules, okay? And so one of the modules they came up with is shear stress in beams. And so that's what we're going to look at. Let's begin. First, we will study shear in rectangular sections. So what you're looking at is a beam with a rectangular cross section. And what I want you to understand is that this area that you see here is not the end of the beam, okay? So this is not the far right end of the beam. No. What we're looking at here is the cross-section area of the beam that you will see when you section the beam at a certain location. So the beam is much longer than this, okay? It runs maybe in that direction, but we have sectioned it here, and the area that you see here is the area that reveals itself once you section the beam at that location. Okay, it's really important that you understand that. Now, when we speak of shear, what we really want to study in this case is the shear stress. And now, the shear stress is the stress that will arise due to the presence of a shear force. Now, in Science N4, you learned how to draw shear force diagrams, and I think you've even been doing that ever since Science N3. And so you will see that when you draw that diagram, you do not always have the same shear force at every location of the beam. It can be changing, okay? At some places it's positive, at some places it's negative, at some places it's got a higher magnitude than at other places. And so if you want to find the shear stress at a certain location of the beam, what you will need to do is first find what is the shear force at that location and use the method I'm going to show you for you to actually determine what is the shear stress at that specific location. And so let's say we have a beam like that, and of course we've sectioned it as I explained. And so at this section, it turns out that when you draw the shear force diagram, you find that the shear force is acting down like that. And in this particular module, we will refer to the shear force as V, capital V. That is what represents the shear force. So you plotted your shear force diagram, and at this particular location, you found that the magnitude of the shear force there is V. Now, because the shear force is acting down, okay, the shear stress that will arise due to that force will also be acting down. But what I want you to notice is that the shear stress does not have the same magnitude everywhere on the cross section, okay? On top here, it's slightly smaller, but here around the neutral axis, it's bigger, and then going down, it becomes small again, okay? So what I want you to be able to appreciate is that the shear stress does not have the same magnitude everywhere on the section, okay? That's really important. When we were doing strength N5, we learned that the equation for the shear stress is equal to the shear force divided by the area that is in shear, okay? But that equation is a general equation, and it will give you the average shear stress on the section, okay? It's gonna give you an average value for the shear stress on the section. But in this module, we will begin to find specific values for the shear stress at specific locations on the section, okay? So the equation you learned in strength N5, that only gave you the average shear stress, okay? What you will get if you summed up all the shear stresses and divided it by the number of shear stresses, if you can think of it that way. It's a rough way of explaining it, okay? A bit rough to explain it that way, but you know what an average is. So this equation here was to give us the average value of the shear stress. But in this module, we're gonna be more specific, We will study the value of the shear stress at specific locations on the cross section, and that is not going to be equal to the average shear stress of the whole section. Okay, but the equation that you were given was that average shear stress was equal to shear force divided by the area in shear. And here, as I said, the shear force will use the letter V and not F. So it's going to be V divided by A. So in some of the questions you can get, they will ask you to find the magnitude of the average shear stress. What you will need to do is take the magnitude of the shear force and divide it by the area, okay, the area in shear, okay, really important. You must divide by the total area in shear. Good. So now, let's say you have to find the shear stress at this location, okay, where you see that line. Let's say you get a question and they ask you what is the magnitude of the shear stress at this location. First, you need to understand what we mean when we ask you to find the shear stress at that location. Really, what we mean is that we want you to tell us what is the shear stress on this plane, because the magnitude of the shear stress on this horizontal plane is the same everywhere. So when you get a question where they say find the magnitude of the shear stress, maybe, I don't know, 200 millimeters from the top surface of the beam, and so that will mean you need to find the magnitude of the shear stress on the horizontal plane that is 200 millimeters from the top of the beam. Okay, so if you go 200 millimeters from the top going down and you draw a horizontal line and then that plane that you get there, the shear stress, the magnitude of the shear stress anywhere on that plane, that is what we are looking for. Okay, so as you can see, it was drawn like that. Okay, you just had the line here and they ask you what is the magnitude of the shear stress on this line, but what is really meant by that is the magnitude of the shear stress on the horizontal plane here. Okay, very important to understand that. And so let us look at a segment of material. You can see here there is a small square where my pointer is. You can see that small purple square here. Okay, and so let us study this small segment of material. So I am going to zoom in and present it to you. So this is the material that we have there. Okay, and you can see on top of the material you have a red line to represent the red line from the horizontal plane where we're trying to find the shear stress. Okay, so that is that line here. Okay, so we're looking at that material, that square segment or square element of material, if you can think of it that way. And so that red line on top is the red line that you have here. It represents the plane where we're trying to actually find the magnitude of the shear stress. Now, for this particular element to be in equilibrium, we will want our shear stresses to have directions as follow, because we already know, okay, that on this side of that segment of material, or should I say on that element of material, okay, on this side we know that the direction of the shear stress is down. That is why here on that side it is down. Now, therefore, if you want it to be in equilibrium, okay, on this side you will want your shear stress to be up, okay, and on this side, therefore, if it is down, at the bottom here it must be to the right, and therefore on the horizontal plane, which is on top here where we're trying to find our shear stress, it must be pointed in that direction. Okay, this is just for the sake of you to understand what is really meant when they ask you to find the shear stress at a specific location on the cross section. Okay, but now we will look at it closely with equations so that you will know what are the steps that you need to take. Now, we're looking at the cross section of the beam. So what you see here, okay, is that area there. So that's what you're looking at here. And of course, it's a rectangular cross section, therefore its neutral axis is right through the middle, okay, and that's because that's where the centroid is. And this neutral axis is the XX neutral axis, which is the one that is the stronger one against bending.